Every bridge you cross, every phone in your hand, every car on the road, someone engineered it, designed it. Built it from nothing but raw metal, heat, and human intelligence. On Tech Today, we go deep into the science of how things are made, how industries work, and the engineering that quietly powers the modern world. From steel mills to semiconductors, from ancient metallurgy to the future of manufacturing. If you're curious about how the world is actually built, you're in the right place. Welcome to Tech Today.
All right, let's dive right in. Today we're going on a pretty incredible journey. We're going to see how a simple idea, just lines of code, transforms into the physical blueprint for one of the most complex things humanity has ever built, a modern RAM chip. But to really get a feel for the scale we're talking about, I want you to imagine something. Let's say your job is to design a massive city, a sprawling metropolis with over 10 billion individual buildings. Just think about that for a second. The planning, the complexity, it sounds pretty much impossible, right? Well, here's the kicker. In our world, those buildings, they're actually transistors. And this entire mind-bogglingly complex city has to fit onto a tiny piece of silicon smaller than your fingertip. That, right there, is the challenge of designing a memory chip today. And no, that number is not an exaggeration. A modern DRAM chip really does have over 10 billion transistors. With numbers this huge, trying to design one by hand, transistor by transistor, it's not just hard, it is physically impossible for any person or even a huge team of people. So how on earth do they pull it off? The answer is a field called electronic design automation, or EDA for short. The best way to think about EDA tools is as these incredibly powerful specialized compilers. They take a high-level description of what you want the chip to do, and they automatically figure out how to turn that into a physical blueprint that's pretty much guaranteed to work. Okay, so we've established the problem. We need to create this impossibly complex blueprint, and we know that EDA software is the tool for the job. But what's the actual process? How does it all work, step by step? Well, this entire journey, it doesn't start with drawings or schematics, not anymore. It starts with code. This is the first major phase, taking a description of what the chip does and turning it into its most basic digital building blocks. And this right here, this is our map for the whole explainer. The process is called the RTL-to-GDSII flow. It's the industry standard pipeline that takes us from register transfer level code, that's the RTL, all the way to the final GDSI file, which is the actual blueprint that gets sent to the factory. Now this is a really key point, and it kind of shatters a common myth. Chip designers today aren't hunched over a desk drawing tiny little wires. They're actually a type of software engineer. They write code in special hardware description languages, like Verilog, to literally describe the chip's logic and behavior. So after the code is written and simulated to make sure it's correct, we get to a step that honestly feels like magic. It's called logic synthesis. An EDA tool takes that behavioral Verilog code and compiles it down into something called a netlist. And a netlist is basically just a giant list of millions of simple standard logic gates, your basic ands, nors, and flip-flops, and a map of how they're all connected to each other. But just when you think this whole thing is completely automated and run by smart compilers, the story takes a really fascinating twist. Because it turns out that the most critical, most sensitive parts of a RAM chip, well, they can't be designed this way at all. This quote from the source material really says it all. It tells us that for the absolute heart of the memory, we're talking the tiny cells that hold the data and the super sensitive amplifiers that read it, our high-level descriptive code just isn't good enough. And this really shows you the two different worlds living inside one chip. You have the digital parts, like the command decoders that are handled by that automated flow we just talked about, but then you have the analog core, the memory array itself, which is basically handcrafted. It's more like art than automation. It's where expert engineers design circuits transistor by transistor, using their intuition to squeeze out every last drop of performance and reliability. So we've got our automatically generated logic gates from the compiler, and we've got our handcrafted analog blocks from the artists. The next huge task is to give all of this a physical form. It's time to actually build our Silicon City. This is where that logical netlist becomes a physical layout, in a process often just called place and route. It starts with floor planning, which is like zoning the city, deciding where the big neighborhoods go. Then comes placement, where every single one of those millions of gates gets assigned an exact coordinate. After that, a perfectly balanced clock signal is distributed to synchronize the whole chip. And finally, routing connects everything together with an incredibly complex web of tiny metal wires. Now, here's the thing. A chip can't just work on a good day, when it's 72 degrees. It has to work flawlessly, whether it's in a freezing cold data center or inside a blazing hot smartphone in the middle of the desert. That level of reliability is verified using a process called static timing analysis, or STA. So how do they guarantee it works everywhere? It's fascinating. They don't just check one normal operating condition. They test the design at the absolute extremes, what they call PVT corners. That's for process, voltage, and temperature. They'll test it slow and hot, which is the worst case for speed, and then they'll test it fast and cold, which can cause other problems, like signals racing each other. It's exactly like testing a jet wing at every extreme of its flight envelope to make absolutely sure it never ever fails. And that brings us to the final stage. This is where the stakes are incredibly high and there is absolutely zero room for error. The design is pretty much done, but before it gets sent out the door, it has to pass the last, most intense checks. There are two absolutely non-negotiable checks here. First is the design rule check, or DRC. The factory has literally thousands of rules about things like how wide a wire can be or how close two things can get, and the DRC tool checks every single one. The second is layout versus schematic, or LVS. This one confirms that the physical city we just built is an exact electrical match to the original blueprint. No mistakes are allowed, period. Okay, so once DRC and LVS are totally clean, the moment of truth arrives. The final digital blueprint, which is a massive file called a GDSII, is sent to the manufacturing plant. This is the point of no return. It's a huge milestone known in the industry as tape-out.
So why all the stress? Why is tape-out such a big deal? Because of this number, the mask set, which you can think of as the set of ultra-precise stencils used to actually build the chip, can cost up to $15 million for a cutting-edge chip. If you find a bug after this point, it's a catastrophic multi-million-dollar failure.
So we've seen this whole incredible journey, from a line of code to a physical blueprint. It's this beautiful dance between powerful automation and meticulous human artistry. Which leaves us with one last question to chew on. In an age where software can do so much, why does the most critical part of this high-tech component, the very core where our data lives and breathes, still depend on the intuition, the experience, and the craft of a human designer?